Hello everyone. Today's video we're going to talk about the relation between distributed computing and special relativity. This is the first of a series of videos where I'm going to be talking about the connections between physics and computing. So in this series of videos we're going to be talking we're going to talk about the kind of the general structures that lies in different physical systems and how to relate them with some of the structures that appear in several computational systems. For today's video in particular, we're going to be talking about the notion of reference frames and observers that come from physics and relate them with the notion of network of computers, of central clock, of global clock, and decentralized system or distributed system. In particular, for today's video, you need to have some sort of grasp of special relativity. I will leave a video in the description, but you need to have some conceptual understanding of special relativity. And for distributed computing, the understanding much weaker because nowadays we all have kind of an intuitive understanding of how kind of a computation pipeline works, especially if you programmed before. So let's get started. And so how are we going to approach this? So basically, we might experiment a little bit how to approach each one of the videos that we're going to talk about. But for today's video, I decided to approach it this way. So within any paradigm in science, we have a set of questions that we are allowed to ask and a set of questions that we are not allowed to ask. For example, I'll have a very popular example in physics is the notion that in quantum mechanics we are not able to answer this question. Are we able to measure momentum and position at an instant of time, what is commonly called the Heisenberg uncertainties principle? So in quantum mechanics, this has a no answer. And however, in Newtonian mechanics, we are able to do this. We are able to measure both momentum and position at an instant of time. So, having said this, how are we going to approach now the topic of today, that is about distributed computation and special relativity? So the way we're going to do it is that we're going to consider two fundamental questions that actually lie kind of deep in the kind of like deep in the structures in special relativity and in distributed computations. So the first question we're going to talk about is related with clock synchronization. So let's first start with talking about these questions in the framework of special relativity, but as we will see later, they are very much kind of ingrained in both of these frameworks. So the first question is going to talk about clock synchronization, and is basically the question if I am able to synchronize two different clocks in different parts of space-time. And this is a key question in special relativity because it also kind of is a prerequisite for the second question, and is if I am able in fact to synchronize two clocks in different parts of space-time, am I also able to say that an event was simultaneous for those two clocks? So the notion of simultaneity. And in fact, it just so happens that in special relativity, here let's put special relativity. I am able to synchronize two different clocks in space-time, or you can also say, are you able to synchronize two clocks in different reference frames in different parts of space-time? And the answer is yes. However, it is also, I think, very popularly known that one event is not simultaneous but for two different observers in special relativity. So this has a no answer. So the simultaneity does not hold in general in special relativity for two different observers. And however, we know that in Newtonian mechanics this is in fact the case, because as we know in our daily life, we are able to synchronize clocks, and we also tend to notice that events are simultaneous. But this is in fact not the case in a special relativity. So these are kind of the tables that we're going to start doing. So a little detail also, this notion of clock synchronization is also known as kind of the fact that you are able to extend the notion of time and space for a reference frame to infinitely far away. So it's also known as that, and we're going to use that later on. So continuing this, we're going. So what does any of these two questions has to do with distributed systems? I mean, they are very fun by themselves, right? But are they at all related with a distributed system? And it turns out that yes. Both questions, in fact, have very kind of direct analogs for a distributed system. So here we're going to write for physics, and here for computation. So the first one is about clock synchronization, and for the distributed computing, what is the analogy? So imagine now that you have a network of computers, that each of them can only communicate with each other by sending messages, and of course reading the messages. So there is this problem in distributed computing known as a centralized clock, or how do you define a global clock in this system of computers? So this is the question, is in fact if you can synchronize a global notion of a clock in a set of computers. Or you can also talk, instead of computers, you can talk about processes. So it's like synchronization of local clocks. So this is also known as kind of the global clock problem. By the way, so if you want a little bit more of information with this, the topic I'm going to be talking about today, so this kind of is mostly the main reference for today's video is gonna be the paper by Leslie Lamport in 1978 that is called Time Ordering and Distributed Systems. So if you want more information, look at the paper, but also this is very much kind of my very own personal perspective with kind of related with more modern topics that we're going to start to be looking later in other videos. So that was the first question, And in fact, this kind of synchronization of local clocks is in fact equivalent. It can be shown to be equivalent to to if you can set up a global ordering of events. And this is in fact a very important question, and is if you are able to order events that happened kind of in the timeline of a network of computers. If you are in fact able to say that each of the events was before and each event was later. So that's for the first question. The second question is also related, and is as we said, is about the simultaneity of an event for two observers, and this also has an analog, and is if are two events that are being executed concurrently, are the two events being kind of executed simultaneously. So it's kind of the like simultaneity of execution. So these are kind of the two questions that we're going to look at in and that are kind of the foundation of this video, or the topics talked in this video. So let's do our little table again, and let's talk about the first question, the second question, because we have not talked about whether if one is able to do this in fact in a general distributed system. And you might have some guess about if this is possible or not, but maybe you will be surprised, because in fact it is not in general possible to set up a kind of a global order, or kind of synchronize all your clocks in a general distributed system, and with a caveat that this is possible to do if we use physical clocks. So, and what is a physical clock and what is a logical clock? So basically, a logical clock is simply a counter that, for example, counts each time there is kind of a change in the program. But a physical clock is, of course, kind of the time kind of the time arrow that we experience in kind of in the universe. And the question too about simultaneity is also not true. Like two events will not be necessarily simultaneous, two concurrent events. And as we know, this is in fact yes here, no for simultaneity, and yes here and yes here. So if we see there is a big kind of relation between these two, and that is actually not very evident at the beginning, because in fact this is kind of yes-ish, this is yes, this is yes, this is no, no, and yes. So there is something kind of the structure there is might be similar, you know, and this is what we're going to be exploring today, and and these two questions are related to two fundamental concepts. So the two concepts are in fact, let's just scroll a little bit, are in fact, with question 1 we have the notion of causality. About, so like this is kind of a little bit perhaps not very related, but we will see where that comes from. So if we see here, we have kind of in physics and in computation, uh, let's do a glossary first of terms, and then we will talk about them in a more kind of geometrical fashion. So in physics we have the notion of something that is called light separated, and something that is called space separated, or space-like or like. Let's do it like this. And in computation we have a direct analog. There is like two events are comparable and two events are concurrent. So this is really important. We will kind of analyze them a little bit later. In question 2, we have also kind of so what is the concept in the question 2? So the question 2 is of course simultaneity, right? And in physics, here in computation. So for physics, what is the key concept is gonna be the concept of a Lorentz transformation, or a change of coordinates in kind of with all four space-time coordinates. So it's gonna be about Lorentz transformation. And in computation is going to be about execution order. Yeah. So all right. So basically, yeah. So there's a little detail I want to say here, and is that of course this execution order, once you set it up, like is kind of is kind of a detail that you have to first set your reference frame in kind of in order to know if something has happened. You have to first set what two reference frames are you comparing with. So in the same sense, you have to set up two different execution orders to see if things happened at the same time or happened in a different time. Okay. Let's continue. And what we're so what we're going to analyze now is like the causal structure of what happens in physics and what happens in computation. So let's first kind of try to analyze about the first concept of causality. What's happening in physics? So what is the key element of special relativity? It is kind of the geometry of it, right? Then if we, for example, have here a kind of a space-time diagram, and so here is time, which is gonna be in years, and space, which is gonna be in light years. Oops. Yes, here light years. Then and if we have a massive particle that is moving, then there's gonna be kind of inherent to this massive particle, there's gonna be the very famous kind kind of light cone, right? And this light cone defines the causal structure. Oops, not very good drawing. Defines the causal structure of kind of the kind of or separates the space-time. So in some sense, we have here what is called the future. This is going to be the past, but also kind of the icon also separate space in what we talked about before. That is the notion of something that is like kind of events that are like and events that are space-like here outside of these light cones. So imagine that that this light cone follows, so whatever is here is going to be like, and for here is going to be space-like or space-like separated. And these kind of green lines are going to be like kind of light particles, right? That light or particles that move at the speed of light. So this is the causal structure of of um, of a special relativity, and we will see that this causal structure is in fact also present in a distributed system. So what is kind of the key element? The key element is that one is able to extend his notion or his reference frame, his notion of causality to all to infinitely far away. So for example, if I have an observer here, and if he has kind of a, let's say as a kind of a mental experiment, as a thought experiment, if he has kind of like rods that are infinitely far away in the three kind of orthogonal directions, and each of the clocks have a clock, then we will extend this infinitely far away. Then we are able in fact to extend this reference frame to all space. Oops. And this is gonna be a particle of light. So this is kind of a classical construction, but the important here is that in fact one is able to synchronize among all the clocks that are in this kind of mental experiment. One is able to make sense of all the kind of all the measurements that happen far away, and in some sense the important thing is kind of this causal structure, because this causal structure is what is kind of the reality for this observer. So this is kind of the important thing. And let's try to analyze this for a distributed system. So here we're gonna talk about computation, and for computation I actually have drawn a diagram before, so I'm going to copy this diagram and I'm going to explain it to you what it is, because it takes a little time to draw, but I'll explain it, no worries. So let's paste it here. Alright, so this is what's happening in computation. So what is this diagram? So we need to explain a little bit more. So here we have a set of processes. So imagine like this is process 1, process 2, process 3, so process 4, etc. until process 9. So we have a network of 9 computers that are executing kind of each of them kind of on their own are executing a program, are doing a computation step by step. So, and these kind of blue lines are kind of messages sent from one computer to the other. So for example, if we have here computer number 3, then at this time step, it sends instead a message such to computer number 4 and to computer number 2. So here then in fact we have process 3, here is process 4, and this one is process 2. So then basically like from process 4 it sends a message to process 3, and then it goes on and it goes on. So these computers are able to send messages to each other, and each of these red events is kind of like a computation, local computation. So here let's kind of pay attention in this red dot that I'm going to let's say paint in magenta here. So, and it's gonna be this here, the same, right? So it's gonna be magenta. And so what happens with this one? It happens that whatever happened in this event is going to affect all these the following events. It's going to have a causal relationship with all these other events that are in fact connected with it, and this is gonna define a region that is denoted here in green. And this region is in fact what we're going to call the comparable region and the concurrent region. So as we said before, there is this notion of like separated and comparable and space like and concurrent. So in this sense, whatever is inside the region, in the green region, is gonna be the comparable, and whatever is outside is gonna be the concurrent. So in principle, if you think about it, this event has no causal connection with any of the events outside of this kind of causal cone. Then they can either be executed before or afterwards. It doesn't matter, and this is going to be key for the notion of simultaneity. And kind of this is what is called kind of concurrency in distributed computing. So yeah, and of course here we have kind of that the time is kind of running in this direction, is going in the kind of in the upwards direction. Right. So what is the catch here? And this is kind of the catch, and is that one is not able to extend the notion of causality for all events. That means that one is not able to compare if this is in fact like it happened before this magenta, if like a certain event in the concurrent region happened before or afterwards. So in principle, one is not able to define a global notion of a clock by only kind of analyzing kind of each of the local clocks, and this is in fact key. But as we kind of said before, if one has a notion of a physical clock, one is able to do it, and this is very well outlined in Leslie Lamport's paper. But we're not going to go in detail here. It's just kind of like to see that in fact the geometry is in fact the same, the causal structure is in fact the same, and that if one is able in fact to extend the notion of clocks to everywhere in this process time kind of um, uh, diagram, then one is able to in fact have the same structure as in special relativity. Okay, let's continue here, and we're going to talk about the notion of simultaneity. So this is kind of a very common thing to talk about in physics, but not much talk about in distributed computing. So questions of universal simultaneity are not allowed, right? Because you don't really know what happened before or afterwards. So what are the kind of the common constructions that one usually see in physics? So the common constructions that one usually see in physics are kind of that one have it's the normal kind of space-time, and one have one observer, and of course there is the line of the light cone here, and as we said before, one is able to extend this reference frame to all space-time. So let's call this reference frame number 1 to kind of to decide what happened, to kind of make sense of the world, right? So one is able in fact to extend this reference frame as we did before with our kind of mental dog experiment. And for example, if we have two events that happen, like let's say this is an event called B, and this is an event called here A, then clearly A is before B in our reference frame. However, and here comes the key, in this second reference frame, things are going to happen very differently. So we have here or let's say the first one, the first kind of the same set of axes, but we have a different reference frame. Oops. We have kind of a reference frame that is kind of traveling at a constant velocity with respect to the other reference frame. So we have here t prime and here x prime. As we know, the only thing that is constant is the light speed. And we are also able to kind of extend the notion of time and space in this other reference frame. And let's consider the same thing that happened before. We have an event B and an event A, but what happened now? Look that B is under the axis x prime. So B is happened before A. So look what happened. This is the kind of the violation of simultaneity, kind of the common construction that one sees in special relativity. And we're going to see the analogous in distributed computing. So what is the analogous in distributed computing? Let's now look at like computing, and I already have the I already have the diagrams here because they are a little bit long to draw. They are here. Alrighty. So let's explain them now. Then it's the same as before. We have kind of time moving forwards this way, and here too. But look what happened. So we have kind of, now we will find a well-defined ordering events for each of the process 2, process 3, and process 4. And we defined a well-defined order here. So what happens first, what happens second, what happened third. So clearly these 3 happen at the same time, these other 3 things happen at the same time, and these other 3 things happen at the same time. Clearly this kind of the magenta one that we draw before happened before this one and this one here. They happened before all the ones in the second kind of execution order. But now let's suppose we kind of do a transformation of process and time kind of space, and it's a very similar thing to the Lorentz transformation, and this is not a coincidence, in fact. So let's call it update order 1 and update order 2. So we have here the first execution order. Oh, I haven't noticed that is not very well kind of it's not very well explained, so let me move this. Sorry about that. Sorry about this. It's not very well kind of shown here because my camera is here, so let me move this to other place. Let me move this up here. Yeah, and also let's copy the execution order. Let's copy this, the time, and now of course the execution order changed, right? So first, second, second, third, now we have fourth, and we have fifth. So this is what happens now. Now we have the first one here, or magenta, but time has been kind of shifted, right? Time is had been stretched, and now effectively, if we looked at let's say 2 different events, let's put this in light blue. Let's say we say, oops, no, not this. Let's say this event in blue, we're gonna call it B, and let's say this event in A. Here, clearly A is before B, but now, if we see here, we have A, which is exactly the same one, the one that is pointing out, and we have B, the one that is pointing out this way. Then B is in fact before A. No, let's write it here. Which is remarkable, right? It's exactly the same thing. Well, not exactly the same thing, but exactly the same phenomena. And this is truly kind of impressive in my point of view, that we have kind of the same phenomena in kind of in a very different kind of field, you know. And this is truly remarkable. And I'm going to end up kind of talking about some of the possible extensions of this. So this is kind of an extra, perhaps not, let's say, not 100% related, but these are kind of weakenings of the notion of simultaneity, of local order, or of global order, sorry, and that in distributed computing, and a weakening of kind of the extension of the reference frame infinitely far away. So let's consider this as a question 0, and now we have in physics the notion that kind of we only have a local coordinate frame. So, and we, if you guys maybe know a little bit of general relativity, you know what this extension means. And in fact, in distributed computing, well, this is exactly the notion that holds, and is the notion of a local order, or what's called a pre-order of events. And this is really interesting because, as we said, as I point out before, in general relativity, in distributed systems, in special relativity, and in Newtonian mechanics, this question 0 has a yes answer. So these two notions of question 0 have in fact a yes answer in this table, and this is really cool. So basically, this is the end of the video. I just want to say that this is kind of a remarkable thing, that we have kind of this, let's say, kind of discrete structure having the same properties as this continuous structure that we devised in two totally different ways. And in fact, here maybe we can complete this diagram, saying that this kind of global order of events, let's put it from another color, with this one is in fact maybe able to define something like discrete special relativity, and perhaps one is able to come back here with a notion of homogenization, but I'm not going to get into those details. But this kind of shows that there might be kind of a underlying discrete structure which you homogenize, and then you obtain the continuous structure. Uh, this is topic for another video, and I hope you enjoy this, and goodbye.